All right, so today we are going deep on penicillin.
Yeah.
Penicillin, the OG wonder drug.
Uh-huh.
We've got research here looking at everything from how it's made, how it works, why it's still such a big deal even today. So think of this deep dive as your cheat sheet to, really understanding penicillin.
It's a story that just, I think, really highlights accidental genius, but then massive scale-up effort. Like, this is really what changed the game for medicine, I think.
Yeah.
So we'll be looking at, how it went from a forgotten petri dish to, like, full-scale factory production.
Okay.
Thanks to, the pioneers like Fleming, Florey, Chain, and Heatley.
Okay, so let's start at the very beginning. It sounds like this whole thing starts with some real microscopic heroes, right?
Definitely. So while it was Alexander Fleming who first, saw what Penicillium notatum could do, it turned out there was another fungus, Penicillin chrysogenum. That became the real, like, workhorse for mass production. And the crazy thing is, scientists figured out how to basically breed these fungi to make them even better at cranking out the drug. It's like evolution, but on fast forward.
Evolution on fast forward. Wow.
Human-driven.
That's wild. Okay, so we've got the right chef in the kitchen, so to speak. So how do we get this chef to, like, cook up huge batches of penicillin? I know it involves something called fermentation, right?
Exactly.
It sounds like brewing beer, but, like, on a mega scale.
Yeah, it really is. It's a lot like that. Submerged fermentation is what we call it. And that's where you grow, the penicillin grows, in these giant tanks of liquid, kind of constantly stirred up.
Yeah.
But here's the thing. Penicillin isn't actually made while the fungus is busy growing.
Right.
Yeah, it's what we call a secondary metabolite, meaning it's produced mainly in the stationary phase. So that's, after the main growth spurt's over, like the fungus is producing its special compounds once it's, settled in a bit.
Okay, so a post-growth bonus that saves lives. Amazing. So what goes into this, like, microbial soup, I guess, that helps encourage the production?
Well, it's all about giving the fungus the right food, essentially.
Okay.
The main carbon source is usually lactose, a sugar that's a little slower to digest. This helps prevent something called catabolite repression.
Okay.
If the fungus gets too much easy sugar, like glucose, it won't be as motivated to make penicillin.
Interesting.
We also use corn steep liquor, which gives it nitrogen and a bunch of other growth boosters. It's like a nutrient-packed broth.
Got it. And I know there are also these, what we call precursors, like PAA and POA. What do they do?
Oh, yeah, those are super important. They're basically building blocks that the fungus uses to actually build the penicillin molecule. So phenylacetic acid, PAA, leads to penicillin G, which is the most common form.
Okay.
While phenoxyacetic acid, POA, results in penicillin V, that one's often better for taking orally.
I see.
So it's like, giving their chef specific flavorings to make different dishes. We also need to manage minerals like phosphate, actually limiting it during production to encourage penicillin synthesis.
Oh, interesting.
And of course, we've got sulfate in there too.
Okay, so we've talked about the right ingredients being key. What about the environment? What conditions does this fungal factory need to actually thrive in?
Oh, it's very controlled, very precise.
Okay.
We use something called a fed batch process, carefully adding more carbon in those precursor molecules over time. The fungus is also, like us, it needs a lot of oxygen, so aeration is crucial. Temperature is kept constant, right around 25 to 27 degrees Celsius. And the pH, or acidity, needs to be kept slightly acidic during production.
Wow, so a lot of close monitoring. You wouldn't want to stress out the workforce. What about mixing and the way the fungus is actually, like, physically growing in there?
Right, well, mixing is key, obviously, because we make sure everything gets enough nutrients and oxygen.
Okay.
But we also have to be gentle, because the fungus can be damaged if you stir too hard.
Yeah, makes sense.
Now, ideally, we want the fungus to grow as individual filaments, kind of spread out. That's what we call dispersed mycelial growth. We don't want it clumping into dense pellets, because that can actually slow down production.
Okay.
And, today's facilities use really sophisticated computer systems, SCADA systems, to monitor and control everything. Oxygen levels, feeding rates, the whole 9 yards.
So we go from this, like, massive tank of fungal broth. How do we actually isolate the penicillin?
Right. So penicillin is what we call extracellular, meaning it's secreted by the fungus.
Okay.
So the first step is actually pretty simple. We just filter out the fungal cells. Then we do something called solvent extraction. At a low pH, penicillin is more stable in its acid form, so we use organic solvents to pull it out of the broth, like separating oil and water almost. This is often done with something called countercurrent extraction, which is really efficient.
Okay, so you're pulling it from one liquid to another. What happens next?
So then we transfer the penicillin back into a water-based solution at a higher pH, and that converts it into a salt, like potassium penicillin, which is more stable. Then we can precipitate or crystallize this salt out by adding some other compounds and cooling everything down.
I see.
These crystals are filtered out, washed to remove impurities, and finally dried and formulated into the different medicines that, we all know and use today.
Wow, it's a pretty incredible journey from like this microscopic organism to an injection that can save your life.
It really is.
And speaking of saving lives, what kind of impact has penicillin actually had on medicine?
I mean, it's been revolutionary. There's no other word for it. It works against a huge range of bacteria, especially the gram-positive types and even some gram-negative ones.
Right.
It's been absolutely essential for treating everything from like pneumonia and strep throat to much more serious conditions like meningitis and even preventing infections during surgery.
Wow.
And historically, it was a key weapon against sexually transmitted infections. Although resistance is becoming a big challenge there these days. It's even used in veterinary medicine.
So it really is hard to overstate its importance. But you did mention resistance, and that is a worrying trend, isn't it?
Oh, absolutely. Bacteria are always evolving, and their ability to develop resistance to antibiotics like penicillin is a really serious threat. It's a global health challenge.
Right.
This is why we constantly need more research, and it's why responsible antibiotic use is so important.
Definitely. So we've traced the whole incredible path of penicillin from, kind of a lucky break in the lab to this complex industrial process, and it still underpins so much of modern medicine. It's incredible. But considering how intricate it is to make this drug and the ever-evolving challenge of antibiotic resistance, what do you think are the most important areas of focus for the future of, treating bacterial infections? What are your thoughts on that?
It's a tough question. But I think we need innovation on multiple fronts, discovering new antimicrobials and also developing strategies to, outsmart resistance.
Yeah, it's definitely something to think about.
Absolutely.
That's fascinating. Well, thank you so much for coming on the show and talking us through all of that.
My pleasure. Thanks for having me.
That was a great deep dive on penicillin. Thanks for listening, everybody.